BeThere is a proof-of-concept system that simulates a mobile communication device of the future with multiple integrated depth sensors. Our proof-of-concept system is composed of a mobile smartphone, a side-facing short-range depth sensor to capture spatial gestures, a rear-facing depth sensor to capture the environment, and a touch strip for clutching. The hardware is instrumented on a monopod to provide additional support for our users. To demonstrate the BeThere concept, imagine a local user Bob who is in need of assistance constructing a model out of wooden blocks. Bob calls Alice, who is an expert model builder. With BeThere, Bob captures and shares a local 3D representation of his environment with Alice. Alice performs gestures on the side of her mobile device to remotely help Bob with the construction, allowing Alice to get a sense of 3D presence. For example, here, Alice is controlling a virtual 3D hand to work with Bob on creating a model out of wooden blocks. BeThere can also be used in other scenarios, such as when a local user like Bob needs help fixing a printer. Here, a remote user like Alice helps Bob figure out what's wrong by pointing at specific trouble spots. The BeThere concept follows 3 steps: capturing the environment, enabling independent viewpoints, and performing spatial gestures around the device. To capture a 3D representation of a local user's environment, BeThere uses Connect Fusion. This approach allows users to perform ad hoc on-the-go capture of their environment by simply moving the device around the physical space. To create an independent viewpoint, a remote user uses the device motion of their camera to navigate the local user's shared environment. BeThere supports dynamically generated depth maps for independent views without requiring the remote user to be physically present with a depth camera. BeThere allows users to perform spatial input to interact in a shared 3D environment. Here, we show a simple 3D pointing technique that can be activated by tapping the touch sensor, allowing the position and orientation of the finger to be used as input. Here, we show how we use a simple pointing technique to control the helping hand, a virtual proxy representation of a physical hand. To control the helping hand, the user performs a pointing technique while holding the touch sensor, allowing the position and orientation of the finger to be used for input. When the user rotates their finger to point upward, the orientation of the virtual hand matches the orientation of the user's finger. A supporting surface structure can also be used to create a physically realistic interaction. Here we show a 3D hand that is unable to go below a table, mimicking physical interactions in our environment. To support spatial input, first our system must track a user's finger. BeThere uses a depth-based approach that extracts fingertip and finger pipe features for ad hoc finger tracking, requiring no calibration or tracking of our system. To test the BeThere system, we conducted a preliminary user study in which groups of 2 participants were asked to help each other in constructing a model out of wooden blocks. Each participant of a group was asked to build a model and were subsequently told to remove 3 blocks required to complete the construction. The models were then exchanged to simulate a local user requiring the help of a remote user. Importantly, this allowed both participants to take turns playing the part of a remote user. To provide assistance, each participant used a pointing technique to control the helping hand. Here, we show example construction results of our user study, demonstrating that participants can perform a simple pointing technique to help construct objects of complex geometrical structure. In addition to pointing, we developed a variety of spatial input techniques to explore other applications that can benefit from 3D mobile communication. For example, here a local and remote user discuss the decor of a physical desk. Users can place virtual 3D objects like this lamp and control its position, orientation, and size. For this scenario, we created a variety of spatial input techniques to allow a user to transform virtual 3D objects. Here, we show our pinch point technique, which enables a user to both clutch and perform a gesture simultaneously. Users can activate the pinch point by bringing their non-extended finger and thumb together, while the extended finger's position and orientation are used for input. Here, we show a 2-finger span technique, where a user can move their index finger and thumb simultaneously along the X, Y, and Z dimensions for fine-grained control of a virtual object. These techniques can be used to perform additional transformation operations on 3D virtual objects like this lamp. In addition to using a pointing technique to control the position of the lamp, users can rotate a virtual object on top of a surface using a pinch point technique. To adjust the scale of an object, users can perform a 2-finger span oriented along the X, Y, and Z dimensions. In another application, here a remote user controls a 3D virtual character to play an augmented reality game with a local user. Here, a user performs a pinch point technique to control the animated ogre. When the user moves their finger up, the character jumps on top of the tabletop. Discrete touch interactions such as tapping the touch sensor can be used to activate and swing the ogre's swords. The system also supports non-physically realistic interactions, which allows the virtual character to move up walls, creating new augmented reality experiences on our mobile devices. Please see the paper for more details.